we're assuming cutoff, it's 0, right? And saturation is when it's turned on. And we know the current is equal to this K prime W over L times VGS minus VT squared, right? And we can't really change this K, that's given to us. This VGS minus VT is given to us. VGS, for digital circuits, we're going to assume VGS is just the VDD in our case all the time, right? Because we're driving these inputs either to VDD or ground, excuse me, with CMOS circuits. So, and we said we don't really play around with L. We always use the minimum L. So the only thing we play around with is this W, okay? So if we were to figure out the delay of the circuit, this I, well, really, we just need to know what the W's are. Call this the WP and the WN. And that would figure out what the delays, low to high or high to low, is on the output. Everybody okay with that? So if we know WPs and WNs, we can figure out the delays. If we're given a complex circuit like this on the left, if we want to figure out the delays, we really have to look at the different situations and kind of convert it. You know, we want to convert this into this simplified form so that we can figure out the delays. Now, to convert it to the simplified form, we need to know, we're going to generate what's called the effective W. Different situations here, different signal configurations will give an effective WP and an effective WN. So I'll call those like W effective. So let's look at this circuit on, which will we do first? Let's look at the P channels first. There are, did I draw it the same way as it's over here? Let's just make sure. C, D, B. Oh yeah, they just had the A on the other side. That's fine. There's several current paths here, right? You could have B is a 1, so there's no path through here, and then the current just goes through A. So then you would have just one transistor, the current going through this A transistor to pull the output high. Or you could have, that's one possibility. You could have the A input high, the B input low, and the D input low, and then you would go through just the D and the B. You could also go through the C and the B, or you could go through both the C and the D and the B. So there's actually 1, 2, 3, there's 4 possibilities of current flowing to pull this Z high. So let's just look at an example. Let's say we just had the first one I said. We're just going through A. W effective, call it for the P, would just be equal to the W of A, right? And we can figure out the current. Let's say, so that's the first path. There's 4 of them, right? Let's try the second one. So now the A signal is high, so there's no current going through here. Let's go to this left one. The C is, A is equal to 1, C is equal to 0, D is equal to 1, and B is equal to 0. So now the current is going right down through here, just through the C and the B, okay? What would, and oh, just to make things a little simpler, I'm going to assume all the transistors have the same W for here, okay? So WP, all the transistors have WP. So in this case, it's WA, but we'll just call it WP. But all the transistors have WP. So in case 2, what would be W effective? Well, to figure that out, you have to realize if I take 2 transistors in series, it's kind of like 2 resistors in series, right? And you would expect that kind of increases the resistance and decreases the current, because you can see here, I is proportional to W. I think we did this analysis before, right? And the we know that V equals IR, right? So the resistance is equal to V over I, or the resistance is proportional to 1 over I, right? So the resistance is proportional to 1 over W, right? Because I and W are directly proportional. Resistance is inversely proportional to I, so it's inversely proportional to W. And what that means is it's kind of like conductance. If you say two transistors in series like that, you would say, oh, if we were doing resistances, we would just say, you know, it would be R1 plus R2. But for conductances or widths, it would say 1 over W total equals 1 over W1 plus 1 over W2, right? Or we can say W total equals W1 times W2 over W1 plus W2, right? So in series, the widths add up like conductances. And in parallel, if I have two transistors in parallel like this, you would say the resistances add up like 1 over R total is 1 over 1, but the widths just add together.
So they behave like capacitances.
Yeah, they like capacitances, exactly. So, and we're going to assume all the transistors have the same W. So in this case, W total would just be 2W, right, P. And in this case, if I had them in series like this, this goes like 2WP, or sorry, WP squared over 2WP, right? Which just cancels there, and you just get WP over 2, right? You know, if you take two resistors in parallel, like if I take two resistors in parallel, and this is R and this is R, the total resistance is half, right? It's just R over 2. And if I take 3, it's like R over 3 and so on. So when they're the same size and parallel, it's kind of easy to calculate. That's why I'm assuming these W's are the same, just to make the calculation easier. Make sense? So getting back to here to our case, I'm going through two transistors of the same W. So the W effective equals, it's going to be WP over 2. It's got half the width, so effectively like half the current. And let's just erase some of the stuff here. Make some room. Yeah, I can do that stuff. Case 3 would be like, now instead of going through, let's make a different color here. I have my swatch here. My swatch. Case 3 would be down through D and B. Well, that's not a very nice color. Let's make it redder. Right? And again, I'd have two transistors in series, so W effective would be WP over 2. And then the last case, I have both of these paths on. Oh, actually, I missed one. There's another case. There's 5 cases. There's a case when all paths are on. So the case 4 was it C is 0, D is 0, B is 0, and A is 1. So now I'm going through both of these paths. So now this W effective. So first off, I have these two in parallel. And so that would be like, if I look at these two, their W effective would be I'd add them. So it'd be like 2WP, right? And then I have this 2WP is in series with this W. So then I get 1 over W total equals 1 over WP plus 1 over 2WP. And what's that? That's going to be equal to WP times WP over 2WP plus WP, which will be equal to 2WP squared over 3WP. And that'll cancel with that, which just equals 2/3 WP. So W effective equals 2/3 WP. Everybody still following me? It's getting late. We only got 3 minutes. We can finish this off. And the last case is, oh, now I've got A equals 0. I'll put this to 0. I'll put my green, and now I got this path. I got 3 paths going through there. So this is case 5. W effective equals. Well, I know from the first 2 paths that was 2/3, right? We already calculate that. So now I'm going to have W effective equals 2/3 WP, right? That was this one, 4. And now I add plus, because it's in parallel, plus WP. So that will equal 5/3 WP. So this is 5/3 WP. So there's all 5 possibilities we did.
Professor,
Yep.
how do you like determine the combinations? Like, for example, how do we know one of the paths isn't that it's going to go through A and then it's going to go through CB or DB? Like, how do we know it's going to go through all 3 on the left side?
So to make a current path to the output, like, this output is, say, charging up this capacitor, I have to have all the transistors in the path turned on. And in this case, since they're P channels, their inputs have to be 0 to make the path. That's why I put when C is 0, D is 0, B is 0, A is 0, all paths are on. Current can go through here, through here, through here.
Oh, okay.
Does that make sense?
Yeah, it makes sense, but I'm just wondering because when you're determining the different combinations, like for example, how do you know for one of them that A is 0 and then D is 1 and then it goes
Oh,
through
I just arbitrarily chose that. I just said these are all possibilities. I said there's only 5 possibilities for these current paths for this circuit.
Okay, I see.
I just arbitrarily picked those.
Okay.
There's actually there's 1, 2, 3, 4. There's 16 possibilities, right? And there's only 5 different current flow.
Okay.
And these are all the W effectives that I can't calculate for that. So you might be interested in saying, well, what's the worst case? The worst case is what? It's the smallest W effective, which would be this one, right? That's the worst case. And the best case is when all of them are turned on. So the worst case is when I'm going through, these 2 transistors in series. So the most transistors in series of a single path is the worst case. And the best case is when all the transistors are on. So this is the worst. And this is the best. Later on, we're going to see why we're interested in both of these situations. When we do timing analysis later on, we're going to see that both of these are important, the worst case and the best case. Generally speaking, the worst case is more important, but both of them are important, it turns out. Anyway, so if you were designing this circuit and you said, well, it's got to beat a certain, I want a certain delay and I want to make the delay the smallest, I'd have to know what was the worst case. I don't care about these better ones. If I want to make the delay as small as possible, I want to know the worst case delay. That will determine how fast I can run this in terms of frequency. Okay, we kind of ran out of time. It's 9:56. So we will continue on with this next week. Any questions before we go?
I just had a quick question that a couple of the people had in chat too. Again, about the bonus quiz. Apparently a bunch of people uploaded at 9:34 and it's marked as late because the submission time was at 9:33.
No, the submission time was 9:35.
That's
Let's go
odd.
look at that.
Because
Pretty
I think
sure.
my upload was at 9:34 and it says it's late for me.
Four? The heck? Yeah. Come on, I can't. Start. Oh. Can I? Oh, it was 9:34. Oh, I thought I put 9:35. Oh, I don't know. Yeah, so this is like at the beginning of that time. That's when it ends it. I was supposed to put 9:35. So it ended at